Hello and welcome to this presentation describing the secure data storage features of the STM32H5. It will cover the main features of the STM32H5 that enable users to protect sensitive data. It's part of a set of presentation that describe the security mechanisms offered by the STM32H5 and related secure firmware. The following topics are going to be explained. First, an overview of the STM32H5 secure data storage features. Second, the flash interface access control that filters out requests that violate access permissions. Third, the combining of flash interface access control and secure AES coprocessor, or SAES, with derived hardware unique key, or DHUK, to encrypt and decrypt sensitive data. Fourth, the provisioning of keys and firmwares. The flash interface implements the logic necessary to carry out the flash memory operations, program and erase, controlled through the flash registers plus security access control features. The embedded flash memory includes a set of non-volatile option bytes. They're loaded at power on reset and can be read and modified only through configuration registers. A new area called option byte keys is used to store not only cryptographic keys, but also any kind of information like mapping, configuration, etc. The secure storage is tied with SAES and OBK HDPL value set by the system configuration, boot and security or SBS. In order to enforce temporal isolation, boot levels are isolated thanks to the hide protect level or HDPL monotonic counter. The secure storage features 5 non-volatile areas dedicated to secure storage. Areas are protected with HDPL and trust zone. Battery-powered volatile secure storage automatically erased in case of tamper. Write-only key registers in the AES engines, i.e. device 96-bit unique ID and JTAG 32-bit device-specific ID. Secure storage can rely upon SAES engine to encrypt the stored data to benefit of derived hardware unique key or DHUK properties. Data are isolated. All data encrypted and decrypted relying upon SAES and DHUK benefit of the variation of the DHUK for each different isolated area, HDPL 0, 1, 2, 3S, and 3NS. The root hardware unique key, or RHUK, is a non-volatile hardware secret unique per device, allowing anti-cloning protection. All keys encrypted using the SAES and DHUK inherit of the RHUK property, unique per device. The epoch is a counter incremented each time a regression is done, allowing anti-rollback protection. This figure explains the temporal isolation based on hide protection levels, or HDPL, which is implemented as a monotonic counter. It can only be incremented. The various programs involved in boot time and runtime are presented on the right chronologically from bottom to top. The ST Root Secure Service, or RSS, the ST Immutable Root of Trust, or IROT, the ST Updatable Root of Trust, or ST-UROT, or Proprietary 1 UROT, and the Secure Non-Secure Applications. Each of these programs is assigned an HDPL. Access to the hide protection area can be denied by progressing the HDPL level in the system configuration, boot and security, or SBS. For example, the part of the flash containing the RSS becomes hidden when the RSS transitions the HDPL from 0 to 1. The HDPL level can only be cleared by a system reset. There's no means to deactivate the area protected by HDP. The protected HDP area is defined by setting its size using start and end sectors in a similar way as the secure watermark. The current HDPL also determines the access control rules and keys used for encryption and decryption. Secure hide protection, or HDP, is controlled by hide protection levels, or HDPL, used for ARM Platform Security Architecture, or PSA. 3 levels are available to facilitate secure boot process stages isolation. Each level increase blocks access to the lower levels, which only become available again on next reboot. Same mechanism works on smaller scale in dedicated key storage mechanism called the OBK. The area associated with HDPL1, which is blocked by incrementing to level 2, is configured using option bytes. The threshold between HDPL2 and HDPL3 is a volatile setting in flash register called the HDP extension. If the two banks are swapped, the protection defined to physical bank 1 remains on the physical bank 1, unaffected by swapping. The embedded flash memory includes two memory sectors, two 8 KB of secure storage, OB-key only accessible by secure privileged state. OB-key storage can contain any sensitive information, keys of course, but also data, such as mapping information, flag, etc. Contents are protected with a 9-bit error correcting code or ECC. Commands enable the user to swap keys from one sector to the alternate sector. The OB-key storage is split into 5 domains for which access control is determined by current HDPL and epoch value sent to the SAES module. Note that HDPL0 is never accessible to the user application. It's reserved for ST application. Regression from one version to a lower one requires the erasure of the keys related to the lower level. A key feature is that data are never disclosed when opening access with debugger. A partial or full regression is necessary to erase and reprogram the data. This is done automatically by the ST debug authentication or DA library that manages the debug authentication protocol by allowing to securely reopen the debug or to launch regressions on secured products in the field. HDPL0 OB keys are never erased. The figure explains the temporal isolation feature. A code running in HDPL0 can access all HDPLs. A code running in HDPL1 can access HDPL1 to 3. A code running HDPL2 can access HDPL2 and 3. And a code running in HDPL3 secure can access HDPL3 secure and non-secure. A secure storage firmware can be developed to be used in the different HDPLs, HDPL0, 1, 2, and 3. It's key to understand that when such code is executed in a particular HDPL level, if it needs to access another level, then it has to explicitly commit this transition by programming next HDPL and also the epoch to select secure or non-secure. This selection is used for flash interface OB key access control, but also used by the SAES to select different DHUK. This figure represents the data protection performed by the flash security mechanisms based on SAES and DHUK. To distinguish two types of protection mechanisms, the following convention is used. Dotted lines identify mechanisms related to access and debug control. Solid lines identify mechanisms related to anti-replay and anti-rollback. The secure storage firmware selects the context composed of HDPL and secure or non-secure state, which is passed to the hardware key access control unit. This unit selects the OBK HDPL and epoch according to this current context and SBS register settings. OBK HDPL selects the area of secure storage of the flash memory and selects the corresponding DHUK in SAES. The epoch selector has to be set by the application wishing to use the secure storage. SBS epoch S and SBS epoch NS are 24-bit values coming from the flash memory and representing regression counters respectively for secure and non-secure states. Then, data to be stored to flash memory will first be checked against accessible domains, and if no violation is detected, are encrypted according to the selected DHUK. This slide focuses on data protection, SAES, and DHUK to support anti-rollback and anti-replay attacks. The anti-replay protection is guaranteed thanks to the use of the root hardware unique key, or RHUK, to process the SAES DHUK. The anti-rollback protection is guaranteed thanks to the use of one of the two epoch counters to process the SAES DHUK. The RHUK is uniquely programmed by ST in the system flash memory and cannot be erased or reprogrammed. It's a 256 bits value used as an entry by the SAS to process the DHUK. It allows anti-replay feature, as all data encrypted with DHUK will have different values compared to any other devices. Two epoch counters are present, one for non-secure, epoch NS, and one for trust zone, epoch S. They're only accessible by the debug authentication. Epoch NS automatically incremented on partial regression and full regression. Epoch S automatically incremented on full regression. Debug authentication guarantees the incrementation of these counters. Epoch value is used in the process of the DHUK, and these counters allow the support of anti-rollback, as even if data are not erased, they will be no more retrievable. In this slide, we show the combination of the two isolation mechanisms, access control, thanks to the flash and data protection with SAS and DHUK. The current HDPL is used by the flash memory to select the right area and by the SAS when processing the derived key to generate a key derivation related to HDPL context. This figure highlights the access control mechanism present in the flash controller. Option byte keys have to be provisioned in locations of the flash depending on the current HDPL value. Increasing the HDPL hides the locations associated with lower HDPLs. Data to be programmed are encrypted by SAS that receives the DHUK associated with the current HDPL. This slide and the following three explain the OB key temporal isolation mechanism. Assumption for this slide: HDPL 0 access control, all the OB keys are accessible. Assumption for this slide: HDPL 1 access control, only OB keys HDPL 1 to 3 are accessible. Assumption for this slide: HDPL 2 access control, only OB keys HDPL 2 to 3 are accessible. An assumption for this slide: HDPL 3 access control, only OB keys HDPL 3 are accessible. An option byte key can be accessed only if the OBK HDPL set in SBS matches the HDPL associated to the storage offset. If it's not the case, an OBK ERR error is raised. This figure describes the OB key programming sequence. We assume that the current HDPL level is 2. Thus, only the HDPL2 and HDPL3 areas of the OB key memory can be accessed. As previously explained, an OB key can be any sensitive information, not only a key. It's encrypted according to the current DHUK prior to being programmed in the related region of the OB key memory. The STM32H5 lifecycle is designed to support provisioning of the product with up to 3 different parties. The first party is the Immutable Root of Trust, or IROT. The second party is the Secure Operating System and Secure Applications. The third party is the Non-Secure Application. We're differentiating the initial provisioning from the full product provisioning. Typically, for an install with 3 parties, we can consider IROT, firmware and data, to be provisioned in provisioning product state, then to move to IROT provisioned, then Secure OS and Secure Application being installed, then product state passed in TZ closed, then the non-secure application being installed, then product state passed in closed. Initial provisioning is done when the life cycle is either open or provisioning. STM32H5 products are delivered in open state. This state is useful for development but cannot be used for products. The provisioning state allows to manage the provisioning of the product. It allows to launch secure firmware install or bootloader to provision the product. The first case considers that one unique OEM is responsible for the full firmware. All can be provisioned in only one step. The second case considers that 2 different parties are responsible for 2 parts. The first party is responsible for IROT and secure, then the second party is responsible for the non-secure application. The third case is an initial provisioning step including only the IROT, STIROT, or OEM IROT covered by a first third party, but the rest of the system is loaded by 0, 1, or 2 other parties. The Secure Firmware Install, or SFI, is an immutable secure service embedded by STMicroelectronics in the devices. The SFI allows secure and counted installation of OEM firmware in an untrusted production environment, such as OEM contract manufacturer. The confidentiality of the installed images, written either in the internal flash memory or encrypted in an external flash memory, is also protected using the AES. ST recommends to protect all key provisioning, even if the manufacturing is trusted. The figure highlights the contribution of second and possibly third OEM regarding the provisioning of firmwares and keys. In the second case, a second OEM provides the non-secure image. In the third case, a second OEM provides the secure image and keys, while a third OEM provides the non-secure image and keys. This provisioning relies on services offered by the firmware installed during the initial provisioning. These services enable the second and third OEM to update the firmware and to provision keys, which can be achieved in 1 or 2 steps. In case of untrusted manufacturing, initial provisioning should be performed through SFI. In case of trusted manufacturing, a debugger or bootloader can take care of this initial provisioning. The difference between the two approaches is the encryption of all firmwares, OB keys and option bytes when manufacturing is untrusted. Image install requires encryption and therefore keys. Thanks to the HDPL and key storage mechanisms, the HDPL0 can provision all HDPLs. HDPL1 can provision from HDPL1 to HDPL3. HDPL2 can provision from HDPL2 to HDPL3. And HDPL3 can only provision HDPL3. Hardware secure storage control improves the security by isolating programs running at different privilege and security levels. For example, the secure storage firmware that runs in secure privileged state provides services to secure non-privileged applications and non-secure kernel and applications. Hardware secure storage also protects OB keys against accesses and utilization from lower-level HDPLs. It also enables secure provisioning of firmware by different OEMs. This figure illustrates the various ways of provisioning keys. First of all, let's generalize. When we're talking about keys, OB keys, we're also considering data like mapping, configuration, status, etc. Keys and data provisioning can cover initial provisioning, but also updates. Initial provisioning considers 2 kinds of environments. Trusted environment, provisioning done in clear through bootloader or JTAG or SWD interfaces. RSS-lib is used to manage the storage in OB keys. Untrusted environment, provisioning done based on encrypted inputs. This is supported thanks to the Secure Firmware Install, or SFI. Updates are handled by applications. It's up to the application to define the way to provision the data. It's recommended to encrypt data to be provisioned. A dedicated RSS service called RSS-lib data provisioning can be called to provision data. RSS-lib data provisioning receives in input a data buffer and programs it within OB keys. The service programs this buffer either in clear or with encryption. Encryption is only possible when the device supports the crypto engine. ACRC prevents any data and parameters tampering issue. The service also checks that the programming is successful. It can be called through the bootloader. The Secure Firmware Installation, or SFI, supports dedicated areas to manage OB key provisioning. Area O, that allows to manage OB key provisioning using SFI, based on 2 structures detailed on the right of the slide. A regular area encapsulates a subheader present before the area payload. The STM32 Trusted Package Creator is part of the STM32Cube Programmer toolset and allows the generation of secure firmware and modules to be used for STM32 secure programming solutions, including SFI. Thanks for attending this presentation. In addition, you can refer to the following presentations: Security Overview, Lifecycle, and Debug Authentication.